In this video, we're getting an introduction to gases. So here is a table outlining solids, liquids, and gases. You've probably talked about these things, solids, liquids, and gases, in previous classes, but I just want to take a look at some of the properties of gases here. So they take the shape of their container and volume. They're highly compressible, and they flow readily. You can see a nice picture here of these gases flowing readily, going wherever they want. So what type of motion do these particles have? Gases, you can see here in this first one, are something called translative motion, which means they sort of go wherever they want in a straight path. They are present in gases and liquids. We've got rotational and vibrational, and those apply to all three states of matter. Sorry, the rotational is only gases and liquids, but that's not important. You'll notice that so all three types of these motions apply to gases and how they move along. So again, looking at gases here, our types of motions are the three we talked about. The strength of attraction is the weakest of all three. It's essentially no strength of attraction. We'll talk about that in a second. And they are the least organized of any of the states of matter, again, because they go wherever they want. So a couple of other points here is gases have no attractive or repulsive forces for each other. Well, what if they, and that's different because solids and liquids have some attractive forces, as we've seen in other parts of the course. So what would happen to a gas if they had some attractive forces? Well, I guess in theory, gases would sort of collect. They'd be attracted to each other. They get too dense, and maybe they'd fall onto the ground. So you have big clumps of gases floating around or rolling around on the ground, and that does not occur. And that's pretty strange because these are the only particles out there that don't have these attractive or repulsive forces. As well, too, gases are said to have perfectly elastic collisions, which means they don't lose any kinetic energy, and kinetic energy just refers to the energy of motion. So when these particles are in motion and they collide with each other, they just bounce off. They don't lose any of their energy. And again, that is different from any other particle out there because we're used to particles losing their kinetic energy as they move along. And gases just keep on going because if they did lose their kinetic energy, again, when these gases collided with each other, they'd eventually run out of energy and they'd be piled up all over the floor. We know that is not the case. And lastly, the speed at which a gas moves is directly related to its temperature. We're going to explore that a little more here in a second. So I want to look at two factors that affect gases. The first one is pressure. So pressure is the measure of the number of collisions on a surface. So pick any surface, particles hitting at, that's going to represent the pressure. There are four pressure terms that we're going to investigate here, and we're going to need to know. And this is an important conversion factor. So the first one is something in kilopascals. That's what kPa stands for. If you actually go look at the, go Google it, the weather conditions today, one of the things is going to be the barometric pressure, and it's going to be measured in kilopascals. So this 101.3 is like the normal pressure. So because that's normal, or what we say is that's equal to 1 atm, that's 1 atmosphere. So these terms are equal to each other. Now in England, they use pounds per square inch, so a conversion would be 14.7. And the very first barometers, and that's what the picture above shows, they use millimeters of mercury. And so 760 millimeters of mercury would represent normal pressure. That's what's going on here in this picture. Now, one other thing to add, by the way, these are the four terms that we'll be using. We're going to need to be able to convert between them sometimes. It's easy enough. And one little note here is that the mercury, millimeters of mercury, is also seen as 760 bar or torr. It's all the same, just different terms, different part of the world. So let's look at how to convert. So for instance, here's a question. Let's convert 50 kilopascals to psi. So we'll use our technique of writing down what we're trying to find, which is the number of psi. We'll set that equal to the number we know from the question. We'll write in x, and let's not forget about our conversion factor. So this one's about psi, so we're going to need 14.7, and it's about kilopascals, so we're going to need the 101.3. So we'll put our line, and we'll put the 101.3 kilopascals on the bottom, so we can cancel out the kilopascals, and the 14.7 up top. So 50 times 14.7 divided by 101.3 should equal approximately 7.26 psi. A second example here, let's convert the 205 millimeters of mercury to kilopascals. So again, we'll write down what we're trying to find equal to what we know. X conversion factor. So now we're using our 101.3 again, and this time our 760 millimeters of mercury. We'll write the 760 on the bottom so we can do some canceling. 101.3 up top. So 205 times 101.3 divided by 760 should be approximately 27.3 kilopascals. And that is pressure for you. All right, so I want to look at our second factor here, which is temperature. And we're used to temperature being measured in Celsius or potentially in Fahrenheit. There's a problem with both of these. Now, if I asked you to define temperature in your own words, often people say it's how hot or cold something is, and that's not really what we're talking about. Really what temperature is doing is it's measuring the speed of a particle. The faster the particle moves, the hotter it is. The slower the particle moves, the colder it's going to be. So really, in essence, we're measuring kinetic energy, the amount of energy. Now, as I've outlined, or as I've pointed out, we have two scales that we're used to. There's a problem with both of these scales. So our Celsius scale is fine working in the positive direction, but the problem is that Celsius has negative values on it, negative temperatures. And same with Fahrenheit. You can have some negative Fahrenheit values. And negative numbers are going to cause us a problem when we start to do calculations in the next section. We only need temperatures that are above 0, so positive values. So we actually have a new temperature scale you probably haven't heard of that we need to discuss. So temperature is going to be measured in degrees Kelvin. That's this guy. So Kelvin is the new temperature scale. Now the good part is that 1 Kelvin is equal to 1 degree Celsius. They just sort of have different starting points. So absolute zero. At absolute zero, particles do not move and thus have a temperature of 0 Kelvin. So you cannot have a temperature lower than absolute zero. The lowest temperature out there is 0 degrees Kelvin, or 0 Kelvin. Now, at 0 Kelvin, you would technically have a temperature of negative 273.15 degrees Celsius. So again, that is the coldest Celsius temperature you can have. It cannot get any colder. And so what's going to be important for us is our conversion factor here, and we'll check this out in a second, is 273.15 Kelvin is 0 degrees Celsius. I want to interject with a little video now. Let's check that out.
Welcome to the absolute zero hour. Now, we're not going to reach absolute zero, and it's not going to take an hour, but it's kind of a cool name, isn't it?
Okay.
Now, cool is just what I want to talk about today. See, this is a box of ice water. It's as cold as when you put ice in a soda. And here is a ball filled with air, and it's connected to a pressure gauge, an absolute pressure gauge. So the higher the pressure in the ball, the higher the gauge will read. Now, what's pressure? Well, it's like moving molecules. The faster the molecules are going, the higher the gauge will read. And the slower the molecules are going, the lower the gauge will read. Okay, I'm going to move the ball from here to here. Now in here we have dry ice. That's solid carbon dioxide mixed with a little alcohol, so it's still a liquid. Now this is colder than it is anywhere on Earth. This is colder than it is in Antarctica. It's colder than the South Pole. You see the molecules slow down and the gauge reads a lower number. Think of it this way. Here's the old molecule machine. Think of these plastic balls as molecules. And when the machine is going this fast, that's like ice water. So this is like a pressure gauge. And it reads this high when it's in the ice water. Then, when I lower it here, that's the pressure of the dry ice bath. So you see, the slower the molecules are going, the lower the pressure reading. Well, let me ask you this. Suppose there was no motion at all. Molecules completely stopped. Absolutely stopped. Well, that would be what scientists call absolute zero. It would be colder than almost anything you can imagine. And the reason is there'd be no molecular motion whatsoever. So try this. We're going to put the ball of air of science into this special freezer. We're going to imagine that it's going to get very, very cold. Now, could we get to absolute zero? Actually, no. Absolutely no.
What?
If you called a travel agency and said, hey, take me to absolute zero, they'd have to go, we can't. You can't get there. Absolutely not. Isn't that weird? No, why is that? Think of it this way. Here's the ball of air, right? It's pretty cold. It's connected by this tube to this clamp. And this clamp is connected to the base of this refrigerator. And the refrigerator's on the table, and the table's on the floor, and the floor's in the building, and the building is on the earth. So there's always a path for heat to get from the earth, into the building, up onto the floor, up to the table, into the freezer, down this rod, into the ball of air. There's no way for the ball of air to be completely separated from some source of heat. There's always a way for heat to get to the air. You can never quite get to absolute zero. So you can't ever get to absolute zero. Zero. Scientists have gotten within 1,000th of a degree Celsius, but they've never gotten there. And they never will. Absolute zero. Zero is more of an idea than a real thing you can get. We can get within 1,000th of a degree, but we can't quite get there. There's no way. Absolutely no way. But the idea is kind of cool, isn't it? In fact, very cool. Thank you for watching the Absolute Zero Hour.
Lastly, we're going to move on to converting. So let's convert 25 degrees Celsius to Kelvin. This is actually very easy to do. So all you want to do is you want to start with that magic 273.15 Kelvin, and you just want to add whatever value is in the question in terms of Celsius. So 25. So you add them together, and 25 degrees Celsius would be equal to 298.15 kelvins. This also works if you have a negative value. So this conversion also works if we have negative values. So let's convert minus 5 degrees Celsius to Kelvin. Again, we're going to write down our 273.15. That's always our starting point for conversions. And now we're going to add minus 5 to it. So essentially we're subtracting 5. So it goes down to 268.15 kelvins. So that is temperature work in kelvins. Two special sets of conditions. I'm going to refer to these sets of conditions. They were created by scientists just to make some questions easier. So the first one we're looking at is called the standard temperature and pressure, or STP. So if I say a question is at STP, you know two things. You know the temperature we're talking about is 273.15 kelvins, and our pressure is 101.3 kilopascals. So again, if I say a question is at STP, you automatically know these two values here. Now the one problem with these values is that we're talking about 273.15 Kelvin, or 0 degrees Celsius. So for scientists to repeat an experiment at STP conditions, you're basically going to have to do it in a refrigerator. Doesn't seem like that's a very good idea, or that's going to work too well. So scientists came up with a second set of conditions, standard ambient temperature and pressure, SATP. They raised the temperature up to essentially room temperature, or 25 degrees Celsius, and the pressure was changed slightly to 100. So again, if I say a question is at SATP, you need to know these two conditions. And keep in mind, we could make up our own sets of conditions. You can have your own temperature and pressure, as long as you identify it and say, you know, the question we're doing is at such and such temperature and pressure, and it's set in stone, you could do it. So again, these are somewhat arbitrary conditions. But again, if I say questions at either of these two, you know a couple of numbers. Let's get to the homework.